Hello everyone. In this lecture, we want to discuss differentiation rules. So we don't want to find the derivative of a function as a function using first principles. We want to use some sort of shortcut formulas known as differentiation rules to find the derivatives of different functions very quickly. So the first rule is called constant function rule. And in this case, we are going to say, okay, we have a function f of x equals c, where c belongs to the set of real numbers. It's just a constant, and we want to find what the derivative of a constant is. So we're going to use the definition. We're going to say f prime of x is limit of f at x plus h minus f of x over h when h approaches 0. And because the function is f of x equals c, let's say c is like 5, so we have limit of applying c minus c over h when h approaches 0. And here, obviously, because c minus c in the numerator is like absolutely 0, so 0 divided by any number will be 0. And we know that the denominator is never 0. It is only approaching 0. Therefore, this answer is going to be 0, meaning that the derivative of a constant is equal to always 0. So we can write this like this. We can say y equals c, y prime is always 0, and c belongs to the set of real numbers. So this is just one rule we come up with. For example, if y equals like 5, the derivative of 5 is 0. The derivative of negative 2 is 0, so on and so forth. That's the short proof of it. Now, the next rule, differentiation rule, is called power rule. And here we are dealing with different powers of x. So we have x to the exponent of n. N could be any real number. So we're going to say n belongs to a set of real numbers. Imagine x squared, for example, or x cubed, or something like that. These are all power functions. And we're going to say f prime of x equals. Now, to find this derivative, we can use the formula f of x minus f of a over x minus a. We take the limit when x approaches a, of course. And this would be f prime at a, logically speaking. So this is the formula for the derivative of a function at a. And here our function is the power function, x to the exponent of n. So I have to write limit of x to the n minus a to the n over x minus a when x approaches a. So this is what I need to find. But the thing is that here we have x to the exponent of n minus a to the exponent of n in the numerator, which has a factor of x minus a. It is divisible by x minus a. And we can factor x minus a out in the numerator and end up with this relation. For this x to the n minus a to the n, inside the brackets we'll have x to the power of n minus 1, and then we're going to have plus a times x to the exponent of n minus 2 plus a squared x to the power of n minus 3, just like that, all the way up to a to the exponent of n minus 1. Now, this formula, x to the n minus a to the n, can be derived like in different ways. For example, if you have like x squared minus a squared, so that is x minus a times x plus a. That's difference of squares, very famous formula in algebra. And when you have x cubed minus a cubed, again, you have this factor of x minus a in its heart. And we have x squared plus ax plus a squared. And if you have x to the 4 minus a to the 4, again, you have x cubed plus x squared a plus xa squared plus a cubed. So it can be factored like this. And you can just continue all the way x to the 5 minus a to the 5. And no matter what you do, you always have this factor of x minus a times some other polynomial there. So if you do that for like exponents of n. So that's what we get in the numerator. And after we cancel out x minus a from top and bottom, we end up with a limit as x approaches a of x to the n minus 1 plus a times x to the n minus 2, a squared x to the exponent of n minus 3, all the way up to a to the exponent of n minus 1. Now, if you sub in a using direct substitution method, you are going to get a to the exponent of n minus 1 plus a times a to the exponent of n minus 2 plus a squared times a to the exponent of n minus 3, and keep going up to a to the exponent of n minus 1. So all these products are going to give you a to the exponent of n minus 1, believe it or not, because if you add the exponents, like 2 plus n minus 3 would be n minus 1, and all these exponents would be the same thing. And when you think about it, how many terms there are, so when the exponent was 2, we had 2 terms, the exponent was 3, we had 3 terms, the exponent was 4, we had 4 terms. Now that the exponent is n, we do have n terms here, so this is actually n terms. But all of these terms are like one another, so that means that n times n a to the exponent of n minus 1 will be the sum of all these identical terms. So, making long story short, we just proved that f prime at a would be n times a to the exponent of n minus 1, or in other words, if you have x to the exponent of n, then y prime would be n times x to the exponent of n minus 1, or generally speaking, f prime of x would be n times x to the exponent of n minus 1. And here we're saying that n can also be a real number. And the name of this rule is power rule. We just proved it. An example would be y equals x to the exponent of 10, and the derivative is 10 times x to the exponent of 9, for example. Okay? Or if you have a quadratic function, x squared, the derivative would be just 2x. Okay? So that is the second differentiation rule that we proved. These are some examples. An example for the first one, y equals 6. The derivative is 0. Instead of 6, you can use your house number. It doesn't matter. Any constant has a derivative of 0. And after these two rules, we move on to the third differentiation rule. It's called the constant multiple rule. Okay, what is this rule all about? The name is self-explanatory. So we're going to say let g of x equal to c times f of x. Okay? And c is just a constant. It could be like 5 or 6 or whatever. And we're trying to find the derivative of this function g of x. So g prime of x is what we want to find. And g prime of x, by the definition, would be limit of g at x plus h minus g of x all over h when h approaches 0. And now we can do the substitution. It will be limit of c times f at x plus h minus c times f of x all over h when h approaches 0. And then you can factor c out in the numerator. It will be f at x plus h minus f of x all over h when h approaches 0. Now, this is limit of a constant times a function. A quotient is a function for itself. So the constant time limit of a constant times a function is equal to that constant outside the limit times the limit of the function itself. So I can put this c, this constant, outside of the limit, and then multiply it by the limit of that quotient function or whatever we have. And this limit I just wrote here is familiar to you. You have seen this formula many times in the past. This is actually f prime of x. That's the derivative of f of x. So that's going to be c times f prime of x. So what we showed is that if you have y equals c times a function, let's say c times f of x, then the derivative of the function would be again c times the derivative of that function. So it's going to be c times f prime of x, and of course we know that c is a real number. So this is going to be the formula, okay? The name of it is the constant multiple rule. And I can give you an example. If you have, let's say, 7 times x to the power 4, okay? So we're going to say the derivative is going to be 7 times the derivative of x to the power 4 itself, because 7 is just a constant. But what is the derivative of x to the 4 itself? Using power rule, it's going to be 4x cubed. So the final answer is going to be 28x cubed, of course. Okay? So the derivative of 7x to the 4 is going to be 28x cubed, according to the constant multiple rule, which we just proved it. These differentiation rules are like, there's like 10 of them, or maybe I will teach you 10. Some of them in the book, some of them not in the book. I'll also give you some shortcut formulas as well that would make your life easier in future. But for now, 3 differentiation rules we proved, and I gave you some examples. I'll give you more examples in future. What you have to do is to watch this video lecture multiple times. I keep repeating multiple times, and you have to watch it 3 to 5 times on average. And you have to pause it, you have to take notes, you have to rewind the video, and then you have to replay, again pause it multiple times, because the first time you digest these, you can't digest these concepts the first time, because they're difficult, they're like new, I should say. It's not like the past courses that we only talk about different types of functions out there. So because the ideas are brand new in this calculus course, by watching the video lectures only once, you will never understand what is going on. You have to watch them several times. You have to hesitate, you have to pause, you have to think, you have to redo the questions by yourselves. So every video lecture should take about 1 to 2 hours. I know maybe on average the duration of the lecture is like 15 minutes. But it's very compressed. And in order to understand what's happening in that 15 minutes, you have to spend 2 hours. That is a reality. Otherwise, you will only hear things and superficially learn about things, not deeply about them. Okay, so I'm going to continue the next lecture in future, continuing with the differentiation rules. Thank you.